So chapter 20, nuclear chemistry. So for the first 19 chapters of this textbook, we have been dealing with chemical reactions, and we all know all the rules about chemical reactions. And so now we're going to break all those rules and talk about nuclear reactions. And then we're going to talk about the different kinds of nuclear reactions. We're going to balance them. We're going to calculate things like half-life to use that for radiocarbon dating, and then we'll calculate the energy released from a nuclear reaction using the all-famous E equals mc squared equation. So first of all, let's talk about what a nuclear reaction is and why we have it. So you've probably heard of a lot of this terminology, but you probably haven't put it in technical terms. So radioactivity, we've all heard of that term, but we haven't really talked about what exactly is happening on the atomic level during radioactivity. So radioactivity is when there is a spontaneous, meaning it happens on its own, nothing's making it happen, emission of particles or radiation from an unstable nuclei. So the nucleus of the atom, if it is unstable, it will break apart and release radiation. So how do you know if a nucleus is going to be unstable? General, we'll go through some more rules, but in general, very, very large nuclei, the bigger they get, the more unstable they become. Pretty much anything over atomic number of 83 is going to be unstable and radioactive, but we do have some that are less than 83 that are radioactive. Nuclear transmutation refers to the bombardment of nuclei by neutrons, protons, or other nuclei. So this is what triggers a nuclear reaction that is non-spontaneous. So rather than it just decomposing on its own, you hit the nucleus with something that is going to destabilize it and start the nuclear reaction. So comparing chemical reactions versus nuclear reactions. Chemical reactions, we're rearranging the atoms, but we had the golden rule of you had to balance. You have the same number of atoms on each side, the same number of each element on each side, and you cannot change from one element to another. You cannot change that atomic number. But with a nuclear reaction, we are going to change the atomic number, and if we change the atomic number, then it changes the identity of the element. So we are turning one element into another element. So this is the alchemist's dream, being able to turn a sheet metal into gold sort of thing. In chemical reactions, only the electrons are involved in the reactions, only specifically those valence electrons in the outermost orbitals, whereas in a nuclear reaction, the nucleus, so the protons and neutrons, and sometimes the electrons and other subatomic particles are involved in the reaction. In chemical reactions, we know that we can be accompanied by absorbing or releasing energy. So the reaction might heat up or cool down, it might release light. But compared to that, a nuclear reaction, do you think it's going to be similar amounts of energy being released or absorbed, or huge amounts of energy? Huge, very, very large. Nuclear reactions release significantly more energy than a chemical reaction would, which is why we use them to generate electricity. And they're generally more efficient than using a chemical reaction, such as the combustion of fossil fuels or coal, to produce energy. In chemical reaction, we can affect the rate of that reaction by doing things such as changing the temperature, changing the pressure, changing the concentration, adding catalysts. But with a nuclear reaction, that rate of reaction is unaffected by these factors. You can't change the rate of a nuclear reaction by increasing the temperature or by adding a catalyst. So this table is on the bottom of page 924, just comparing the two types of reactions. So when we are writing out these nuclear reactions, because we are changing the atomic number most of the time, we need to show the elements rather than just as C for carbon, B for boron, etc. We need to show them with their atomic numbers and their mass numbers, because the mass number often changes also. So we're going to do that by using the isotope symbols. So way back in chapter 2, we learned about the isotope symbols. To write the isotope symbol for an element, it's the element's symbol, and then the top number here. Oh, go back. Pen. The top number, let me do it over here on helium, sure. The top number is the mass number, A, the mass number, and then the bottom number is Z, the atomic number. So the mass number is the sum of the protons and the neutrons, and the atomic number is just equal to the number of protons. So that was the isotope symbol we did before. So here are some more things we can write isotope symbols for: subatomic particles. So for example, we have talked about, when we talk about protons, we really mean an H plus ion. When we say proton, it's really an H plus ion. So an H plus ion contains what subatomic particles? If it doesn't, what does hydrogen start off containing? One proton and, not hydrogen, that's deuterium, contains a neutron. Normal hydrogen, just normal hydrogen contains one proton and how many neutrons? 0 neutrons, good. And if it's normal hydrogen, it also has an electron, but if it becomes H+, it loses that electron. All you're left with is the proton. So when we say proton, we often give the symbol, the isotope symbol for hydrogen, but we're not including the electrons. This is just going to be the proton. Or we may put a P for proton, so you'll see it written both ways, both with the H and with the P for proton. For a neutron has a mass of 1, but it has no protons, so it has a 0 down below. An electron has a mass of 0. Now, yes, technically electrons have mass, but again, they're like 10,000 times lighter than a proton, so comparatively 0 relative to the mass of a proton. And for the number of protons, because an electron is opposite in charge from a proton, we're going to put a -1 down here. So -1 referring to the fact that it is opposite in charge from a proton. So you can write that as an electron, or sometimes we write that with a B, the B standing for beta particle. So this is a beta particle, or an electron. The main difference between calling it an electron or calling it a beta particle is where it originated from. If it originated from an orbital, an electron cloud, like we've been learning so far with chemical reactions, we just refer to it as an electron. But as we're going to see, we can actually have these particles be released from the nucleus. If a particle that's identical to an electron is released from the nucleus, we're generally going to call it a beta particle, because it didn't come from the electron orbital. It was not released through a chemical reaction, but a nuclear reaction. A positron is the exact same size as an electron, so we're going to put 0 for its mass, but it is positive in charge, as the name positron would suggest. So it's like a positively charged electron. So the only difference there is we're going to put a +1, not just a 1, but a +1 to denote that it has a positive charge down here. And then the last main subatomic particle we deal with in nuclear reactions is an alpha particle. An alpha particle is identical to the nucleus of a helium atom, which is why sometimes you'll see it written this way as helium 4/2. But we're not going to include the electrons. It is not identical to a helium atom. It is identical to a helium nucleus, just the nucleus, so not including the 2 electrons you would usually find on a helium. All right. How do we balance a chemical reaction? We do that by adding coefficients to balance the number of each element on each side. Well, now with a chemical reaction, we can change one element into another. So instead, to balance a chemical reaction, there's 2 things that must be balanced. Number 1, mass. We can't break that law. Mass must be conserved. So the top numbers on our isotope symbols, these top numbers here are our mass numbers. So these numbers must be conserved on both sides of the equation. You can't change your mass. The other thing that must be conserved is the bottom numbers, the atomic numbers, must be balanced on both sides so that the charge is conserved. We can rearrange those charges, but we have to conserve overall the total amount of charge. So the total of all atomic numbers and the total of all mass numbers on both sides, product of reactants, must be balanced. So in general, we're not going to do this by adding coefficients like we did with chemical reactions. Usually with these, I'm going to have some unknown species, either the reactant, the product, or in some cases, the subatomic particle that was involved in the reaction either being released or absorbed in the reaction. and you're identifying the unknown by what is left over as far as what mass and what charges are left over. So, for example, let's go ahead and do an example of this. Identify the missing species in each of the following nuclear equations. So in the first one, I have polonium-208, and it has an atomic number of 84, and it's going to turn into lead-208 with an atomic number of 82 and release some particle X. To identify X, you must first identify its two numbers, its mass number and its atomic number. So first of all, if I'm looking at it here, is the mass here conserved? Oh, wait, there's a typo in here. That should be polonium-212. If you're following along on page 925, this is problem 20.1. Sorry, that was a typo. That should be 212 polonium. All right, so the mass was not conserved. So that must mean that our unknown particle X must contain the missing mass. How many mass units are missing? 4, which means our X must have a mass number of 4 up top. What atomic number down below must it have? 2. Good, because I have 84 on this side and 82, so I'm missing 2. So which subatomic particle has a mass of 4 and an atomic number of 2? The helium, the alpha particle. So sometimes you'll write it as helium, sometimes you'll write it as alpha. They're the same thing. Same thing. All right, for part B, we start with strontium 90 over 38, and we're releasing a beta particle. And now we want to know, well, what did strontium turn into? So whatever strontium turned into, is it going to have the same mass? Yes, because the beta particle has no mass. So X still has a mass of 90. But does it have the same atomic number? No. What must its atomic number be? Good, 39, because it has to balance out. So 39 and -1 have to balance out to that 38. So what element are we? You can give me the symbol. You don't have to pronounce it. Y. Good. Deuterium. So X, the unknown, must be deuterium 90. I'm not even sure if that's how you pronounce it, but that's how I pronounce it. All right, so go ahead and try and do C. Determine what your starting particle is. Everybody got an answer? What element are we? Fluorine, good. And this fluorine has what mass? 18, and what atomic number? 9, good. So, compared to chemical reactions, are nuclear reactions easier or harder to balance? Yeah, most students would say easier. There's not quite as much going back and forth. If I change this coefficient, what else did it change over here? Not so bad. All right, that's it for section 1. Moving on to section 2. So on to page 926, nuclear stability. So in this section, we're going to first talk about patterns of nuclear stability. So I said earlier that general elements over atomic number of 83 are going to be unstable, but we also have unstable elements less than that number. So how can we predict if an element is going to be unstable? And if so, predict what kind of nuclear reaction is it going to undergo? Then we'll talk about nuclear binding energy and calculate how much energy is released in that reaction. All right. So first of all, We know that the nucleus, as it gets bigger and bigger and bigger and bigger, is going to become unstable. So why is that? Well, we can look at the fact that it's very, very, very small, so it's extremely dense because it still contains almost all of an atom's mass. Compared to the mass of an atom, the mass of those electrons outside of the nucleus are teeny tiny flies in the back of an elephant. So let's assume, number-wise, that it contains basically all of the important mass of the atom, but it's extremely small. So let's assume a general nucleus has a radius of 5 times 10 to the negative third picometers and a mass of 1 times 10 to the negative 22 grams. If we calculate the density, mass over volume, and getting the volume from the volume of a sphere, 4/3 pi r cubed, then we get that it has a density of 2 times 10 to the 14 grams per cubic centimeter. All right. So compared to things that we're familiar with the densities of, mercury is something we dealt with back in chapter 10 when we were doing gas laws. It has a density of about 13. That is very, very dense. Water has a density of 1. This has a density of 10 to the 14. So this is significantly more dense than we can even visualize or have a comparison to. That's how dense it is. So it's roughly 10 to the 12 or 9 trillion times more dense than the densest element we are even aware of. Extremely dense. So we know from Coulomb's law was that Q1, Q2 over Q1 times Q2 divided by the density squared. The electrostatic energy, or the force, if you want to say, the force of attraction or repulsion is proportional to Coulomb's law. We know that these charges are going to repel if they are the same charge and attract if they're oppositely charged. Well, in the nucleus, all the particles are either uncharged or positive, which means if you have a whole lot of protons in that nucleus, how are they going to start feeling about each other? How do multiple protons feel about each other? They don't like each other. They're both positively charged. And we said that the nucleus is extremely dense, which means they are extremely close to each other. They've got those neutrons, which are buffers between them, but honestly, when you get that close to each other, that's not going to do a whole lot of good. So once you get a whole lot of protons in there, so a very big atomic number, there's going to be so many protons packed in that teeny tiny nucleus that they're going to start repelling each other, and that's why you're going to end up with the nucleus destabilizing and wanting to break apart to release that. So how do we determine at what point this becomes? Well, we're going to compare this to a ratio of how many neutrons to protons we have. So if we have more neutrons in there than protons, in general, those neutrons can kind of act as buffers between the positively charged protons. So having more neutrons than protons is preferred if you're trying to become stable. Having more protons than neutrons is almost always going to be unstable for that reason. So for stable elements that are very low on the periodic table, less than 20, generally the most stable isotope is one that has a 1-to-1 ratio. So for example, carbon. How many protons are in carbon? 6 protons. So if I have, what's the most common isotope of carbon? Carbon what? Good, carbon 12. How can we know that just looking at the periodic table? The mass number, good. The average mass of carbon is 12.01, which means that the majority of carbon must be carbon 12, which would have how many neutrons? Also 6 neutrons. So that's a 1-to-1 ratio. So that's a pretty stable isotope of carbon. If we mess with that, then it's not going to be stable anymore. So with smaller elements, 1-to-1 keeps it stable. But once we get larger than 20, we're going to need more neutrons in there to buffer around those positively charged protons. So this is, let's see here, starting on the bottom page 926, patterns of nuclear stability, some general rules for predicting if something's going to be stable or not. So the very first rule is called the magic number rule. I know, again, why do we name these things such? But the magic numbers are on the back of your fortune cookie, 2, 8, 20, 50, 82, or 126. Doesn't that sound like the numbers you'd see on the back of fortune cookies, your lucky numbers? So these magic numbers, if you are this many protons or neutrons, then you are generally going to be a very stable, less likely to break apart spontaneously, very stable nucleus. So 2, 8, 20, 50, 82, or 126. These are the magic numbers. After this, it becomes more of trends. Doesn't guarantee you're stable or not, but just tells you you're generally likely to be stable or unstable. So in general, if you have even numbers of both protons and neutrons, such as we saw in carbon-12, you are generally going to be stable. Whereas if you have odd numbers of protons and or neutrons, you're more likely to be unstable. So stability is favored by even numbers. The next trend is the one we already mentioned. Once you get bigger than 83 or more than 83 protons, you're going to be unstable. No matter how many neutrons you have, there's just too many protons packed in that itty-bitty nucleus. They're going to be fighting for space. And then the last rule is very specific. The two most unstable elements are technetium and promethium. These two are always radioactive regardless of what isotope you are. So technetium and promethium. They're always going to be unstable. And this table 20.2 on the bottom of that page goes back to that idea of even and odd numbers and how likely you are to be stable. So on the very bottom of this table, if both the number of protons and neutrons are even, there are 164 stable isotopes when this table was written. I know since this table was written, we have more elements that have been discovered or created, but they haven't really been studied well enough to tell how stable they are. If both of them are odd number of protons and odd number of neutrons, there are very few stable isotopes. And then if you are half and half, an odd number of protons but an even number of neutrons, or vice versa, then there are fewer, but still some at least, stable isotopes. So let's go back to that ratio, that 1-to-1 ratio of protons and neutrons that we said was very, very stable if you are a small element. So this is known as the belt of stability. So I'm looking at the number of protons on the x-axis, the number of neutrons on the y-axis. This straight line right here is where you have a 1-to-1 ratio of them. So down here, below element number 20, in general, your most stable elements are those that are really close to that line, really close to being 1-to-1. As you get bigger than element 20, the line is going to curve up, the belt of stability is going to curve upward, which is saying that you're going to want to have more neutrons than protons in order to stay stable. So for example, here around element number 50, the stable isotopes are over here with about 70 neutrons compared to 50 protons. So the bigger you get, the more neutrons you need padded around those protons to keep them stable. If you are outside of this belt of stability, then you're going to be radioactive in general. And that plot is on the top of page 927. Any questions about that plot? So you can use that to predict whether or not an element is going to be stable. All right. So if you're above that belt of stability, you have too many neutrons. Below that belt, then you have too many protons. So how can we fix this problem? What is the atom going to do to try and get back into that belt? So if it's above the belt, it has too many neutrons. It has to get rid of neutrons. Well, you can't just lose a neutron. They're stuck in the nucleus. It can't just lose in itself. But what it can do is it can lose a subatomic particle such as a beta or positron. So let's look at what happens if we start as a nucleus and we undergo beta particle emission. So that means we release a beta particle. So we start with the nucleus, we'll start with the neutron. So here's our little neutron particle, and we're going to take a tiny, tiny chunk of it and eject that from the atom. That tiny chunk is going to be a beta particle. So the tiny chunk that left is going to have what charge? Negative. So that little piece that left is going to be negatively charged. What do we know about what happens when you lose a negative charge? What are you left with? If you start out neutral and you lose a negative charge, then what are you left with? Are you still neutral? No, you become positively charged. So once it leaves, what is left becomes positively charged, which is the same as a proton. The other thing is mass. Back in chapter 2, when we first learned about the mass of these subatomic particles, we learned that neutrons are slightly heavier than protons, just a teeny bit. If we lose this beta particle, it's going to lose a teeny bit of mass. Not a lot, because electrons are very light, but a teeny tiny bit, enough to have us closer to being the mass of a proton. So what is left is something that is slightly lighter than a neutron and positively charged, which is basically a proton. So if an atom undergoes beta emission, then it is essentially turning a neutron into a proton. If it turns a neutron into a proton, then that shifts that ratio of neutrons to protons. It also shifts the identity of the element to one element to the right. So if you're on the periodic table, just go one element to the right or one atomic number over, and that's your new element. So for example, carbon 14, what do we use carbon 14 for? Dating, good. Radiocarbon dating. So this is when we're trying to figure out how old is a human remains from the, deep in the Mesopotamia or something like that. Really old stuff, not just, somebody who maybe died a few years ago, but somebody who died thousands of years ago, trying to figure out how old they are, how to figure out how old a really old piece of parchment paper is, or a really old piece of cloth is, or something like that. We use radiocarbon dating. So it's carbon 14. When it undergoes beta particle emission, the mass number isn't going to change because beta particles don't have very much mass, but the atomic number is going to go up from 6 up to 7. So the identity changes from carbon 14, which we know is not a stable isotope of carbon, to nitrogen 17. Here's our 14. Nitrogen 14 has a 1-to-1 proton to neutron ratio, and it's less than element number 20, so now we are stable. Other examples of this, potassium turning into calcium, zirconium turning into Nb. So just examples of why you would do this is if your ratio of neutrons to protons is too high, so you have too many neutrons, you're likely to go through beta emission. If you're below the belt, you have the opposite problem. You have too many protons and not enough neutrons. To do this, to release this issue, instead of releasing a beta particle, you're going to release a positron. So you're going to start off being a proton, which is positively charged. See, now there's the little line. Which is positively charged, and that little positively charged particle is going to leave. So if I start off being a proton and I lose my positive charge, what I'm left with is a particle that's about the size of a neutron and is neutrally charged. So basically, beta particle emission turns a proton into a neutron, which is going to make your atomic number go down by 1 unit, so you'll be moving now to the left instead of the right. So examples of this is potassium going to argon. So if you're above the belt of stability, expect to go through, to become stable, expect to go through beta particle emission. Below the belt of stability, expect to go through positron emission. All right. You can also undergo capture. So all that we've been talking about so far is releasing a particle, but an electron can also be captured by the nucleus. Now, this can happen a couple of different ways. This can happen intentionally through electron bombardment, which is how we go about nuclear reactions that we're trying to capture the energy for, such as in a nuclear reactor for a nuclear power plant, or this could happen spontaneously. But basically what happens is when that electron hits the nucleus, it is going to be attracted to a positively charged proton because electrons are negatively charged. that positively charged proton and negatively charged electron collide and combine, and that positive and negative will cancel out. So it essentially turns the proton into a neutron. So this is another way of turning the proton into a neutron if you're below that belt of stability through electron capture. So overall, it's the same change in the element as a positron emission as far as what it changes. It doesn't change the mass number, but it makes the atomic number go down by 1 unit. All right. Let's talk about what that energy is that is released. So how can we measure the energy that's going to be absorbed or released during a nuclear reaction? First thing we're going to do is calculate something called the nuclear binding energy. Now, we talked about binding energy before, back when we were talking about, let's see here, back in Chem 151, we talked about the binding energy W from electrons being released from a metal during the photoelectric effect. So that was chapter 6, the photoelectric effect. But that's to release an electron from the outer shell of a metal atom. Nuclear binding energy is going to have to be destabilizing or breaking apart the nucleus, which is going to release significantly more amounts of energy. So how much energy it takes to break up the nucleus into its protons and neutrons. So first thing we're going to need to know is a difference in mass. So in our E equals mc squared, the m is actually not the mass of the whole atom or even the whole nucleus, but the mass difference. So in general, if you add up your masses of your protons and neutrons using the numbers we learned back in chapter 2 and add up what the nucleus should have a mass of, you'll end up with a mass that is slightly higher than what we actually measure the mass of the nucleus to be. So in general, we have a difference in mass. So for example, let's look at the fluorine-19 isotope, which is the most common isotope of fluorine. It has the atomic mass of 18.99840 atomic mass units. That's what we measure it to be. We know that it has 9 protons and 10 neutrons for a total of 19 nucleons. We know that the mass of a proton, we can calculate that using a hydrogen 1 or hydrogen plus ion, is 1.007825 atomic mass units, and the neutron slightly heavier, coming in at 1.008665. Let me write those off to the side because we're going to need them in a second. So a proton has a mass of 1.007825 AMUs compared to a neutron at 1.008665. So if I wanted to find the mass of fluorine, I would add up 9 times the mass of the proton plus 10 times the mass of the neutron. And when I do this, I come up with a total of 19.15708 atomic mass units. But when I measured the mass of the isotope, I only got 18.99840. So there's a difference in the measured mass versus what we calculate the mass should be, and that's called the mass defect. So the difference in the mass in this case is 0.15868, so the difference in what we calculate versus what we actually measure, and we're going to call that the mass defect. The difference in the mass that's measured, which would have to be given to you, versus what you calculate by adding up your protons and neutrons. Now, to form this isotope, it's going to release energy, release a lot of energy. So it's going to be exothermic, releasing a lot of energy to form this isotope. To calculate exactly how much energy is released, we're going to use that E equals mc squared, but we're going to put in terms of a change. So delta E is equal to delta M, and that's our mass defect that we just calculated. And then what does C stand for? What is C in mc squared? Good, speed of light. So about 3 times 10 to the 8th. We can use more significant figures than that. We're going to use the 2.9979. Right out here. 2.9979. 2458 times 10 to the 8th meters per second. Speed of light. And then delta E is just the idea of the mass energy of the product minus the energy of the reactants. So that's why it's the mass of the product minus the mass of the reactants.
What did you say E was again?
The energy, the nuclear binding energy. All right, so going back to our fluorine 19 example, our delta M we found to be negative 0.15868. So we're going to always end up with a negative mass defect because the actual mass is always going to be less than what we calculate the mass to be. So this 18.998 is our measured, that would be given. This 19.157 should be what we calculated by summing or adding up the protons and neutron masses. So delta M is in atomic mass units. So we need to convert atomic mass units to kilograms because we need these things in SI units. So an atomic mass unit is going to be, there are 6.022 times 10 to the 23rd, or Avogadro's number, atomic mass units per gram. So to go from grams to kilograms is 10 to the 3rd, so that's where this conversion factor comes from. 6.022 times 10 to the 26th atomic mass units per kilogram. So that's just coming from Avogadro's number and then converting grams to kilograms, 10 to the 3rd. So we end up with the delta M in terms of kilograms as being negative 2.6349 times 10 to the negative 28 kilograms. But you see how we calculate it in kilograms? If you're following along in the book, we're currently on the bottom of page 928.
So you said that just combined Avogadro's number and kilograms in one step.
Yes.
So we don't have to do it like that, right? We can separate it?
Yeah.
Because I know I'm going to get confused.
Yes, so if you wanted to separate it, you could say, instead of times this, you could put times 1 gram over Avogadro's number, 6.022 times 10 to the 23rd AMUs, and then times 1 kilogram over 1,000 grams. 1,000, I'm losing a 0. And that's where you'll get the 10 to the 26 from. All right, now to turn this into energy, we just take this and multiply by c, speed of light squared. So that's 2.9979. How many significant figures do they want us to go out by? 2458 times 10 to the 8th meters per second, and we're going to square that. Be careful when you plug this in your calculator, you only square the speed of light. Don't multiply them and then square it. Speed of light gets squared before you multiply it by that change in mass. multiply these together, I'm getting delta E is equal to negative 2.36813 times 10 to the negative 11. And my unit, I have kilograms on the top, meters squared also on the top, and on the bottom, seconds squared. So kilogram meter squared per second squared is also known as a joule, which is our unit of energy. So I could ask you just for the nuclear binding energy, which would be this. This is the nuclear binding energy. I could also ask you for the nuclear binding energy per nucleon. So the energy of that we would have to then calculate. Oh, sorry. First, you could do it per mole. So if you're doing it per mole, you would just multiply it by Avogadro's number to get per mole. Or you could do it per nucleon. Now, nitrogen, or we're doing fluorine. Fluorine 19 has how many nucleons? How many protons and how many neutrons? In nitrogen, or fluorine 19. 9 protons and 10 neutrons for a total of 19 nucleons. A nucleon, again, is just something that is in the nucleus. So more likely I'm going to ask you to calculate what is the binding energy per nucleon. You take that nuclear binding energy, delta E, that we just calculated, and just divide it by the number of nucleons, which is the sum of the protons and neutrons. So for fluorine 19, we would take that delta E and divide by 19 nucleons and get joules per nucleon. In general, the greater the binding energy per nucleon, the more stable the nucleus, because that means how much more energy it is going to take to break that nucleus apart. So the bigger that number, the more likely you're going to be stable. So if we were to compare this, a graph here, as our mass number is increasing down here on the x-axis, here we're comparing the nuclear binding energy per nucleon. And as we can see, as we increase the mass number, the nuclear binding energy per nucleon will also increase. And then it starts decreasing a little bit. There's uranium-238, which we know is not very stable. All right, let's try this out. Iodide. The atomic mass of iodine-127 is 126.904473 atomic mass units. Calculate the nuclear binding energy of this nucleus and then the nuclear binding energy per nucleon. So the first thing we need to do is we need to figure out what that mass defect is. To find the mass defect, we need to figure out the difference in the calculated mass versus the measured mass. So they gave us the measured mass, 126.904473 atomic mass units. Now to calculate what the calculated mass would be, we need to add up the protons and the neutrons. So looking at iodine-127, how many protons are there? 53, good. And how many neutrons? Good, 74. How do we find that? Good. 53 subtracted from 127 is 74. So we're going to take these number of protons and neutrons and multiply by the mass of a proton versus the mass of a nucleon, which I wrote over to the side there from earlier. 1.007825 AMUs versus 1.008665. And then we'll add that up, and that'll give us our total mass. they round to. They just round that to a 4. So to find our mass defect, or delta M, it's going to be the measured that was given in the problem minus the calculated we just calculated. Atomic mass units. So before we can plug this into E equals mc squared, what do we have to do with this mass defect? Good, turn it into kilograms. They go out. All right. So those are delta M in kilograms. What do we need to do next to turn that into a binding energy? Good. Plug it into E equals mc squared, or take this and multiply by c, the speed of light, squared. And that will turn this into delta E for binding energy. Times 10 to the 8th. Whoops. And we get a binding energy of negative 1 point. 0.71847 times 10 to the 10. And this is now in joules. Now, if that's the binding energy, now if I just ask you for the amount of binding energy, you would leave off the negative. It's negative because it's going to be exothermic. But if I'm just asking for the amount of energy, you would just leave off the negative because the amounts can't be negative. If I also ask you in this problem for the nuclear binding energy per nucleon, how many nucleons are in this isotope? Good, 127. So to find the nuclear binding energy per nucleon, we would just take this number and divide by 127 nucleons. And we get 1.0 0.35313 times 10 to the negative 12 joules per nucleon. Any questions about calculating the binding energy? Again, you already know the equation. It's just tedious to find the mass and make sure it's in the right units. But pretty straightforward. Ready to move on? All right. Section 3, radioactive decay. So in radioactive decay, the speed of it, we said, was not going to be affected by things like temperature or the presence of catalyst, but they do still follow the same rules of kinetics that we learned about in chemical reactions as far as calculating the speed of the reaction and calculating the half-life, which we can then use for things such as dating old artifacts. So dating based on radioactive decay. So we know that spontaneous radioactive decay from an unstable isotope is known as radioactivity. That can result in the emission of an alpha particle, beta particle. Another example is releasing gamma rays. Now, we did not in the first section talk about gamma rays so much because gamma rays have no mass and they have no charge. So they're not going to change your atomic number or your mass number. So in balancing, it looks like it doesn't really change it. It just kind of changes the stability of the nucleus without actually changing its mass or its atomic number. But these are very, very high energy compared to alpha or beta particles, radioactivity being released. Very short wavelength, and we learned in chapter 6, the shorter the wavelength, the higher the energy. The emission of positrons or electron capture. And these are all things that can occur naturally. Now, generally, this is going to occur until you reach a stable isotope. And in many cases, it's going to take more than one nuclear reaction before you reach a stable isotope. So, for example, a series of reactions trying to get from an unstable isotope to a stable isotope is known as a radioactive decay series. In this example we show here on the side of page 931 here is starting off with uranium-238 and ending up with lead-206. And look how many different steps it goes through. Some of these steps are very fast, some of them are very slow, and we've given you the half-life here to show you how fast or slow it is. So the first decay is relatively slow. Going from uranium-238 to thorium-234 is releasing an alpha particle, and this takes a half-life of 4.51 times 10 to the 9 years. That's a long time. The next one is a relatively short reaction, very fast. Thorium-234 is going to release a beta particle and turn into Pa-234. This takes 24.1 days for a half-life, or half of it to disintegrate. The next one's even faster, 1.17 minutes. Then we're back to the slower ones for a while. Some of these are actually going to split. For example, when we get down to here to polonium, polonium is going to either release a beta particle and go to At, or in some cases release an alpha particle and go to lead-214. Now, a very small amount, 0.04%, will release a beta particle, but the larger amount will end up being the lead-214. Either way, that can go into bismuth-214. So here's the uranium decay series. I'm not going to ask you to draw out these decay series yourself, just be able to recognize what you're looking at. This is a decay series. It shows you the half-lives of each step and what kind of a nuclear reaction is. If it's beta particle emission, if it's positron capture, et cetera, it's just showing you what happens at each step. So just like with section 1, we have to balance them. For example, that very first one, uranium-238 turning into thorium-234, had to release an alpha particle because otherwise it wouldn't be balanced. When we generally look at this decay, each step of it is going to have something called a parent isotope and a daughter isotope. So this is just terminology. The parent is what you start with. The daughter is what you are left with. So for example, that very first step, the uranium-238 would be the parent, and the thorium-234 is going to be the daughter. So you'll just see these terms being used. These undergo first order kinetics, which we learned about back in chapter 14, first order, second order, third order, etc. We're going to do first order. That's what what radioactive decay follows. So the rate of decay at any time t is going to be given by k, little k, your rate law constant, times n, where n is the number of radioactive nuclei present, or how many of them you have. So by integrating it, we end up here. This is the integrated first order rate law. So that equation is straight out of chapter 14. Natural log of your amount at time t divided by your initial amount is equal to negative kt. That's straight out of chapter 14. And the half-life equation, also straight out of that same table in chapter 14, is 0.693 over k.
So what's the, wait, so the T equals the Kn, how is that?
The, right here,
Yeah,
t,
what's the difference
okay,
between
so,
the two equations?
okay, so this is going into the first equation, and then this is after we've integrated it using calculus.
Okay.
Yeah, which you won't have to integrate yourself. We didn't even have to back in chapter 14. Just the two I put in boxes, the only ones you need. Now, generally, in this case, instead of being given your rate law constant k, you'll be given the half-life, because half-lives are easily measured for these radioactive substances. And right there in the radioactive decay, it told you what the half-life was of each step. From the half-life, you can plug it into the first equation and calculate what k is, your reaction rate constant. Then you can plug that k into the second equation and either determine how much will be remaining after some time t, or if I give you the amount that's left over, calculate t, how long has passed. And that second one is what we use for radiocarbon dating. We know what the half-life is for carbon-14. We can calculate then by how much carbon-14 is left, determine therefore how much time t has gone by. Write these two equations off to the side. Little k, not big K. Big K is the equilibrium constant. So, as I said, we can use this to determine the age of an artifact, the most famous one being carbon-14 dating. So, where does carbon-14 come from if it's such an unstable isotope? We know the most stable isotope of carbon is, of course, carbon-12. Well, it happens just from radiation from the sun hitting nitrogen. And where can we find a lot of nitrogen here on Earth? The air, right? The atmosphere is mostly nitrogen-14. So when the sun, the radiation from the sun, cosmic rays, not just the sun, but also from other stars, hit our atmosphere, they're going to bombard it with neutrons. So neutrons from cosmic rays from the sun and other stars hit our atmosphere. Those neutrons are absorbed by the nitrogen-14 in our atmosphere, turning it into carbon-14 and releasing a proton, a hydrogen. So once we have that carbon-14 is unstable, it's going to decompose back into the more stable nitrogen-14 by releasing a beta particle. We know we can determine what the half-life of this is, and from that we can figure out how much time has gone by. Now, in general, as a living object, we breathe in nitrogen all day long. Even plants do it. Anything that's alive, it does this. They take in air, and that air contains what they need. If we're animals, we're taking in the oxygen. If we're plants, we're taking in the carbon dioxide. But we're also taking in massive amounts of nitrogen. So as we breathe and respirate, we're taking in nitrogen, and some of that nitrogen we're going to take in is going to bring in carbon-14. So at any given time, we're maintaining a specific equilibrium of carbon-14 in our bodies. Whether we're a person or an animal or a tree, we're maintaining a certain amount of carbon-14 just by continuously replenishing it by respiration. Now, what happens to a living thing that would cause it to stop respirating? Death, right? The person dies, the animal dies, somebody cuts down the tree to make some sort of wood object, somebody cuts down the flax to make papyrus paper, Something happens to kill the object. Once it dies, it stops breathing. Once it stops breathing, it stops replenishing its carbon-14. And all the carbon-14 that's in it, that's being decomposed back into nitrogen-14, is not being replenished. So you can measure how much carbon-14 is in an object or an artifact, such as a fossil or an old piece of paper, an old piece of cloth, something like that, and compare it to how much C14 is in a living sample of the same thing. So this is why carbon-14 can only be done on things that were once alive. So you can do it on a piece of paper because that paper was once a plant material. You can do it on a piece of cloth, whether that cloth was made out of wool that once came from a living sheep, or whether it was made from cotton, which was once a plant, and of course you can do it on fossil or bones and such. It just has to be something that was once alive, once respirating and taking in carbon-14. It can't be done on things like rocks or pottery, things like that. It cannot be done unless the pottery was using some sort of plant material to be making it. So let's go ahead and give an example of this. A wooden artifact was found to have a carbon-14 activity of 9.1 disintegrations per second. Given that the carbon-14 activity of an equal mass of fresh cut wood, of I guess the same tree species, has a constant value of 15.2 disintegrations per minute, determine the age of the artifact. So N is going to be instead of the amount here, it's going to be the activity or disintegrations per minute. So this 9.1 disintegrations per minute, that is going to be our N, our activity at time t, while 15.2 here is going to be NO, our activity at time 0. The half-life of carbon-14 is 5,715 years. Determine what T is, the age of the artifact. So remember, we had two equations. We had the integrated rate law for first-order kinetics, and we had the half-life equation. So what's the first thing that we're going to do with the given information? Good, find K. Take this, that is our T1/2, our half-life, which is equal to 0.693 over K, and use that to determine what K is. I'm getting 1.21 times 10 to the negative 4. Two, 1, 3, sure. Times 10 to the negative 4. What's going to be my unit here? Is that 4 not showing up? Hello, it's a 4. What will be the unit for K here? If we rearrange this equation, we get that K is equal to 0.9, why do I keep on flipping? 0.693 divided by the half-life. Right? Our half-life was in what unit? Years. So what is our unit for K? Good. Years to the negative 1, or reciprocal years. That's going to be our half-life. All right, now that we have K, we can plug it into our integrated rate law. Natural log of NT, which is going to be that 9.1 disintegrations per second, divided by our initial activity, N0, which is the 15.2, is equal to negative K times T, and we now know that K is 1.213 times 10 to the negative 4. Reciprocal years times T. So what we're solving for here is T. So what do we get for a T? T is how many years? Good. 4,230. We've only got two Snibben figures, so we're just going to do 4.2 times 10 to the third. And that is the age of our artifact. Carbon dating cannot be used for objects that go older than about 10 half-lives, because at that point there's so little carbon-14 that is not really measurable. So carbon-14 dating is useful for things that are between about 1,000 years old and about 60,000 years old. If you're fresher than that, you're probably haven't disintegrated enough to be making a noticeable change. If you're older than 60,000, you probably have so little carbon-14 left that it's not an immeasurable amount. So what if you are something that aren't living? Well, if you're not living, say you're looking at a rock, instead you need something that decays that's found in rocks, and a good example of that is uranium-238. So uranium dating can be used to measure the age of something that is not living, such as a rock. So you're trying to figure out how old a strata is on the Earth that you need to dig down or something like that. Uranium, because it has a half-life of 4.51 times 10 to the 9th years, can be used to date significantly older things than carbon dating, plus it's used for things that are not living. But it's still going to be the same general process here. All right, so today we're out of time, but we got pretty far.